When your system starts up, there are two files that the bootloader loads. One is the Linux kernel, called starts with VMLINUZ for virtual mode, meaning it's a compressed file. That's the important thing about this video. And there's an init ramfs file, which is also a compressed file. Now, init ramfs compressed file, like other compressed files, you use some decompression like gzip or something like that. But the interesting thing about the Linux kernel is part of it's uncompressed, ready to go, ready to execute, and part of it is compressed. Today, we're going to look at the code that decompresses its own file. It loads up and boots, and then it does this function called extract kernel. And that's where we're going, is how does that extract kernel work? Startup 64 is still in the uncompressed mode. And we're going to quickly get to the point where we extract the kernel. But before we get there, let's just kind of review a little bit. We went all the way from 16-bit to 64-bit mode in a previous video. And now what I'm doing is going through here and see anything that refers to compression. Compute the decompressed kernel start address. Then there's some more details about that, but that's what we're doing here, is computing that target address to relocate for decompression. Talks about paging mode down here, some other details. Now that we've done our calculations, we can pass these calculated values for the output target address. We have to know where to put it in memory. We call the function extract kernel. Let's take a little bit here and see if there's any information that might be interesting. The compressed kernel image has been moved so that its position is against the end of the buffer used to hold the uncompressed kernel image, and the execution environment, which makes sure there is room to do the in-place decompression. Then it says look at another file. But here's a nice little chart here where they show that the uncompressed kernel image and then the compressed kernel image. We'll study that a little bit more. If you want to freeze the video and read through that and study it, that's okay. I'm going to move on. Here's extract kernel. See some more housekeeping here before we do something. Here we actually do a console init. So remember, we're still in the uncompressed mode, but we're going to do a console here so that we can finally do some debug early console in extract kernel. Validate memory location choices. So we still haven't done the decompression, because if we don't do it right, everything is going to crash. Here we have something going to the console, decompressing Linux. So it's actually taking place now. Our next really important value here is the function pointer decompress kernel. Diving deeper, here's the decompressed kernel, some free memory calculations, and underscore decompress. We find this function now called within decompress kernel, called just decompress, and this ends up being in another file. We arrive at underscore decompress, and note that it is UNLZ4. So this is Unix LZ4, which is considered today to be the fastest decompression method for Linux. So that's what I chose here. There's various others that could be used. If you wanted to create a distribution, you could use gzip or various other choices. So I'm using LZ4 considering that's the most modern. Within that first function underscore decompress, this file is chosen for the LZ4. So we go to unlz4, Unix LZ4 decompression, and here are the specific details of that. Now remember, we're moving from one memory location to another, so there is very specific low level code in here to keep straight all those details. There's not a lot to see. If we want to go through and do it byte by byte, we can follow through on that, but I'm not going to do that. I thought this would be deep enough for now. Now that we've got the kernel completely decompressed, we're ready to run the kernel. In other words, we got to that a lot earlier than in my video, which was called underscore start to do idle. But now I'm at the point where we've decompressed the kernel, but there's one other really important file to decompress, and that is the init RAM FS or init RAM file system. What's created early on to make things easy and fast is rather than go directly to a file system on the hard drive, we create a file system in RAM. So it acts just like a drive. We mount the drive, we read the files in the drive, but it's all in RAM. We haven't actually accessed the disk itself. Now, of course, the disk is there, but we're all in RAM as far as the Unix thing is concerned. Who put us in here and who started us up? Well, that was the bootloader. And once the bootloader started us up, then we're all in the RAM space because it unloaded the file and executed it and did all those neat things. So now I want to find out where in the heck this init RAM FS file is decompressed. Where better to start than the file called init RAM FS? Here's where it all starts. Populate root file system. So the root file system will actually be in this RAM disk. Now, something very curious goes on here. There's a function called async schedule domain. So this is an asynchronous thing where we're going to start this routine up, the do populate root file system. We're going to start that up and but not hold off on running other things going on in the code. So the kernel can continue to initialize while this thing is doing its work. Here's the function that we've launched asynchronously. So we've done that because it takes a little bit of time to do some of the operations that are coming up. Here it says load the built-in init RAM file system. So we're going to unpack. Now, guess what the unpack to root file system does? That does the decompression. So let's go at least take a look at this and see if we can find the decompression part. Now we're in this unpack thing that's going to help us figure out where the decompression is. So I'm going to try to do a fast track through all of this. Down here, we get to this decompress equals decompress method. And what this decompress method does is it finds out what kind of compression was used, whether it's gzip or what was going on. So let me go quickly to this decompress method. The decompress method looks at magic numbers and determines whether it's what kind of file format it's going to be. Here are the choices. The LZ4 was what the kernel was compressed in. A partial bit of the kernel was compressed. And we'll find out that init RAM FS uses the gzip. Now that we've determined the decompression method, we can now actually start to do that. And down here, this function x right is where the action really happens. So it goes from the start to the end. So this gives it the limits that it has to go. Well, this is actually the size of the file that we're actually going to decompress. Now that we've finished the unpacked root file system, assuming there's no error, we move on to this part down here and we do a final step here where we flush the file put, and let's see where we end up. There's another function here, wait for init RAM file system, that's used by the kernel to make, or the start kernel command, to make sure that it doesn't go ahead before this is all unpacked and ready to go. Again, more code details, which I love, but it might not be the best way for you to learn. But anyway, what we've done is we've decompressed what? The kernel itself. Part of the kernel we unpacked and we decompressed it. And then there was the init RAM FS. That happened to be gzip. And we did the same thing. We ran an asynchronous process while the kernel's doing all its initialization stuff. And when it's ready, that little function says wait. When we're done waiting, then we can go ahead and start using the RAM disk. Now, maybe we should mount the RAM disk so we see what's going on. We can start doing scheduling.